All right, you guys. Well, we already took a look at how to do integration by parts, and it turns out that that is a powerful tool. However, there are a lot of instances, as you all know, there are types of problems that are almost recognition. There are shortcuts to them if you can just find a particular format. Well, there's no exception with good old the integration by parts. We call this the tabular method. There is a tabular method that goes to integration by parts. So if I give you a specific type of integral, now it has to look just like this. There has to be two functions within the integral, one of which, let's call it the f of x term. Again, order doesn't matter for these, but repeated derivation of this f of x term, or one of your functions, has to result in 0. That's often, and if not exclusively for our purposes, a polynomial. So, x cubed, x to the 5th, x to the 7th, something that if you keep taking a derivative, you'll end up getting 0 eventually. Then g of x has to be something you can integrate. No, I'm not messing up here. The first function I'm talking about, derivation, take a derivative of f of x until it gets to 0. And in g of x, we need the integration that repeatedly can basically go on indefinitely, at least for the duration of, the derivatives that happen in f of x. The idea is, I think you get the idea, when we did integration by parts, you notice there was a combination of derivatives and integrals back and forth, and it can repeat. Well, this process, this tabular method, allows for that repeating that commonly occurs in this circumstance. Basically, polynomial times some function you can take the integral of repeatedly. So let's keep going. Here's how we set this up. The tabular method implies table. The table is set up where you take the derivatives of the f of x function on the left, and you take the integrals of the g of x function on the right. This all stops when you get to 0 with your derivatives of f of x. So then the end result of our integral is actually the sum of the products, an alternating sign of these values that we put in the table. So we're basically going to do products of the values in the table in a certain fashion. I'll show you in a minute. And then we're going to sum them up with alternating signs. That means we're going to basically go add a positive, add a negative, add a positive, add a negative. That means we're going to have plus minus between these products. So that's a preview. I'm going to show you in person here, so hang in there. Here's an example. X cubed times e to the x. F of x is that x cubed, which is a polynomial, something we could take the derivative of and end up with 0 eventually. E of x is something we can integrate indefinitely. In fact, we can continue to take the integral of e to the x and we'll get e to the x. So now here goes. I'm going to run through those real fast until we get to 0. Stop when your f of x function, the derivative, is 0. Now, the way we do the products between the terms on the left and the right is diagonally. So here are actually the 4 terms that are going to be, or 4 products that are actually going to show up in our integral result that we're shooting for. So the derivative, or the integral of this function that we have, f of x times g of x, or x cubed times e to the x, is going to be the product of these 4 things you see in the diagonal. The only difference is we're going to see them alternate positive and negative, and we're going to add them all up. So here it goes. So here's the integral of that function. It's equal to, right here are the 4 terms, 4 products that you see the diagonal lines indicating. Now the first one will be positive, second negative, third positive, fourth negative. Here it is. Ta-da! We're done. And that is the tabular method. It really zips you through the process of doing this specific type of integral that we traditionally do by integration by parts. Hope that helps, and look forward to showing you more soon.